Okay, great. Hopefully everyone can see me. Oh, there we go. I can see myself. Okay, so I will be your MC tonight. My name is Karina. I am a third-year graduate student in Professor Jeff Filippini's lab. Jeff is an assistant professor of physics here at the University of Illinois. He works on experimental cosmology projects, which in less fancy science words means that he designs and builds experiments that are geared towards studying the very early universe. And for reasons that I am sure he will get into, one of the best ways to do this is to put telescopes on balloons and fly them very, very high. If you have any questions, feel free to put them in the chat. I'll be monitoring that. I'll be relaying any questions that you have to Jeff. And then we will also have a time for asking some questions at the end of the talk. Okay. I think that's it. So Jeff, I will let you take it from here.
Okay. Well, thanks, Karina. Hope folks can hear me. Welcome to Astronomy on Tap for May of 2021. In our unusual virtual format we've been using the past few months, many months, but we hope we're on our way out of one of these days. So what I thought I'd talk to you today about is, as Karina said, something that I and my group work on, which is astronomy from balloons. And many of you may be familiar with, of course, astronomy from the ground. We have telescopes. You may have a telescope. You may have seen telescopes. You know that there are big observatories on mountains around the world. And there are some telescopes in space, things like the Hubble Space Telescope, or soon the James Webb Space Telescope, the Chandra X-ray Telescope. And ballooning kind of fills a niche in between. And so what I want to tell you a bit about is why we do this kind of crazy thing. What kinds of science we get out of it, and what the experience of doing it is like. So if I get started here, this is my other version of the title slide. So this is the view from a balloon, from a stratospheric balloon over Antarctica. This is a payload called Spider that I and some of my group members work on, looking back at the Earth. And you can see that this is a space-like environment. The sky is black, not blue. You're above over 99% of the atmosphere. Most of the curvature you see here isn't the curvature of the Earth. We're not quite that high, but we're at about 120,000 feet up, about 37 kilometers or so. And most of this is lens distortion, but this is from a GoPro camera, so literally a ski helmet camera that was bolted to the payload. And I'll tell you a bit more about that. But this is, we are in the blackness of space, even though there is a little wisp of atmosphere still above us. So to start off, if we're going to talk about why we want to be on a balloon, we have to talk about why we want to be above the atmosphere. And the atmosphere, of course, is very good to us. It gives us air to breathe. It's we're big fans of the atmosphere. But for astronomy, it can be problematic because it blocks the light of the universe and the other things from the universe that we wish to study. Now, of course, you and I, as humans, look at the universe with visible light. And in visible light, the atmosphere isn't half bad. If you get outside of the lights of a big city, or the outside of Champaign, outside of whatever town you may be in, and get out maybe into the cornfields, into the mountains, into a park on a clear night, you can see a remarkably clear view of the sky in visible light. Countless stars, the band down the middle is the glow of our own Milky Way galaxy that we're embedded in. Astronomy works really well in visible light. The atmosphere, the air above us, is very, very transparent at the wavelengths, at the kinds of light that we are able to see with our eyes. And that's how we got astronomy, is because conveniently enough, our eyes respond to the light that the sun is good at making, and the atmosphere is very transparent to that. So we get to see the universe this way. But there are more kinds of light and more ways to see the universe. And other Astronomy on Tap talks may have spoken about some of this. This is a rendition from NASA of the electromagnetic spectrum. You can think of it as all the different colors of light, including the colors you can't see. So this is a busy graph So I want to kind of focus in on a couple of things. Oops. See here, we're getting to me being unable to use this despite all this. Okay, so the sun, the sun is shining mostly in visible light. So let's first look at the bottom part of this graph over here someplace. So this is telling you the visible light, the rainbow that we're used to seeing, is the light is a wave, an electromagnetic wave. So electric and magnetic fields rippling back and forth very fast and moving through space. That's what we detect. Instead of ripples in a pond, it's ripples in the electric and magnetic fields of the universe. That's what we see. But visible light is only a very narrow range of that. And these are distinguished, different kinds of light are distinguished by their wavelength, how big each ripple is. So for visible light, those ripples are kind of the size of bacteria. But there are, if you go to longer wavelengths, you get infrared, like heat vision, that's emitted by warm objects, but our eyes don't see. Microwaves, like in your microwave oven. Radio waves, like listening to the car radio or anything like that. Radio waves, or used in the Wi-Fi that this computer is using right now. You can also have wavelengths that are shorter than visible light. The ultraviolet that gives people sunburns. X-rays used for medical imaging to look through your body, and gamma rays that are emitted from radioactivity and from other energetic phenomena. So they're all different colors of light, just colors beyond blue or beyond red. And then if I look at the top part here, this is showing you how transparent the atmosphere is. So in these shaded regions, the atmosphere blocks light from space from getting to us. Whereas in these open regions, including the region of visible light that we can see, the atmosphere lets through the light unobstructed from space. So astronomy from the ground is feasible in these gaps, is only feasible in these gaps. We can look at the universe with visible light, as we do with our eyes, get a really clear view, though we still sometimes want to get to space to avoid twinkling of stars due to atmospheric fluctuations. We can do radio astronomy. We can build big radio dishes that observe the universe that way. But if you want to observe the universe in the infrared, ultraviolet, X-rays, all these other ways that you might want to learn about the universe, the atmosphere gets in your way. And it does so in somewhat different ways. So at the long wavelengths, what's actually happening is the air is the upper layers of the atmosphere are actually reflecting back long wavelength radio waves. At the short end, for X-rays and gamma rays and ultraviolet, the light is so energetic. These rapid vibrations are so energetic, they actually can knock electrons loose from atoms, and that absorbs the X-ray or absorbs the ultraviolet. And so, you've heard of the ozone layer that absorbs ultraviolet. Similar things happen with many molecules all throughout, and so you're blocked from seeing these X-rays, ultraviolet, gamma rays. And then in the middle, in the infrared and microwave wavelengths, that kind of light can be absorbed to set molecules spinning and wiggling, and in various ways. So I have a little animation showing the wiggling of chemical bonds of water and the spinning of a molecule of water, and that's why these wavelengths of light are so well absorbed. So, okay, that's what the atmosphere is doing for us. So let's talk about what we're going to do about it. So the trick of ballooning is to get to the stratosphere, to get to an altitude above the bulk of the atmosphere, about 99%. So this is very high. We're talking about altitudes like up here between around 35 kilometers, 40 kilometers. So that's over 20 miles off the ground. That's much, much higher than the 30,000 feet you might have heard for jet airplanes, 35,000 feet. We're several times higher than that, more like 120,000 feet. So the air is incredibly thin, and that's good for looking up. It's above the clouds, it's above the ozone layer, in fact. It's lower than orbit, it's lower than space, it's lower than where meteors splash, but it's very, very high. And that means there's very little absorption. So I showed you all of those different ways in which molecules of air, and water is particularly good at this, absorb light. And because there's so little air, and particularly extremely little water, you have a clear view of the universe at a wide variety of wavelengths, a wide variety of colors of light. So that's my brief discussion of the atmosphere. And that gets us to the fun part, to ballooning. What are we going to do? How are we going to get up there? Well, the good part about ballooning is that it gives you this sensitivity. It lets you see the sky unobstructed, clear, dark skies at a variety of wavelengths of light that are inaccessible often from the ground. So this is an example of a balloon payload. This is Boomerang showing at launch. So this is the payload. This is a sort of a string that's leading to the balloon, which is about to be released and take Boomerang to the sky. This was around the year 2003, I think. And it's also important that these are fairly cheap. So cheap on the scale of science. So on the scale of projects that take many, many people many years and involve expensive hardware. So Boomerang, over the course of many years, cost a few $1 million. That's a lot of money, but it's not very much compared to sending a satellite to space, which can cost $1 billion. So these are cheap by the standards of access to space. The bad part is that anyone who's worked on a fancy piece of equipment, you don't get to mess with it after it launches. It only gets to be in the air. As you see, it'll only be in the air for hours, days, weeks, whereas a satellite can be up for years. And a ground-based observatory can be up for years. There are very stringent constraints on mass and power. You can't launch arbitrarily heavy things. And the whole thing, like the entire payloads I'll describe generally run on power of about 1,000 watts or so. So kind of like a big hairdryer to run millions of dollars of scientific equipment. It's not easy. And as I said, you don't get to mess with it. It needs to be very autonomous. The system needs to run itself. There are times in the flight where you literally only get to text message back and forth with it. It has very, very little information it can give you. So these are all big challenges. But it's important to note these are the same challenges on a smaller scale faced when you want to send something into space. And that means that's one of the reasons that these are so valuable. Balloons not only do wonderful science in their own right, but they let you prove out technologies to use in future space missions. You get to test things in an environment as close as we can get to space itself. And this is true not just for the parts, but for the people. People who are scientists and engineers and students who get trained working on these kinds of projects are well prepared to work on future balloon missions, future space missions, satellites. There's a long pipeline between these. So for example, Boomerang that I show here that observes the cosmic microwave background, the glow of the early universe. Many technologies developed on that, including this sensor system here called a bolometer. It's a very, very sensitive radiation detector optimized for space. Was tested on a balloon, and given the great success that the Boomerang payload had in making new measurements of the universe, that same technology was then prepared to use some years later in the Planck satellite, which was almost $1 billion mission that really revolutionized our measurements of the microwave background and of the universe and the galaxy. So you are, in addition to doing great science, you're a pathfinder for both technology and people to get you to space. Okay, so what kind of balloons are we talking about here? This is an image taken with an extreme telephoto lens from Antarctica of a balloon launched just before Christmas 2008 of a payload called Anita. This is an instrument that looks, you can see the science instrument is down here. Now that science instrument is, I think, about 15, 20 feet tall. It's quite big. This balloon is enormous. And you can see it's basically transparent. It's very, very thin. And you can see some of the specs here. So the volume of the balloon is about 30 million cubic feet. And I'll give you a sense of what that means in a moment. The film is only 20 microns thick, less than 1,000th of an inch thick. And the whole thing is several hundred feet across when it's fully inflated. So let's talk a bit about that. This is a diagram comparing the size of these balloons that are used for NASA science to other things you might be familiar with. For example, the Washington Monument in Washington, D.C., football field. These are stadium-sized balloons when fully inflated. When they launch, you can see here the payload that you just saw. The payload sits below a parachute that will bring it down after the flight. And the balloon itself, when it's first launched, is like a string. Only the top part is inflated with helium. But as you go up and up and up and up and up in the atmosphere, the air pressure gets less and less and less. So you get closer to space, the air gets thinner. And that means the helium in that balloon will expand and fill out the whole balloon. And this is what it looks like. So about 400 feet tall, almost 500 feet across. These are truly enormous balloons. And they're capable of lifting 3 tons of science payload to 120,000 feet. So these are big numbers. But let's talk about some small numbers. So you're used to probably balloons, like these sort of rubber party balloons. These are quite thick, if you think about it. So you may be used to, you have a balloon like this that's full of helium. A balloon full of helium rises. I mean, this one has actually got too heavy a string on it, but a balloon like this rises because the helium inside it is lighter than air. It's less dense than air. And these balloons are also filled with helium in much the same way. One difference is this balloon, you can see I can squeeze it. It's tough. The pressure inside the balloon is higher than the atmospheric pressure. The helium is squeezed inside, pushing to get out. And we've sealed the bottom of the balloon to keep it tight so that the helium doesn't get out. And as every little kid knows, the helium will eventually leak out by going through the rubber. But this is a system designed to hold the helium in nice and tight. The balloons we're talking about here are what are called zero pressure balloons. They're actually open at the bottom because a balloon this big, there's no way, the helium inside is actually kept at basically the same pressure as outside. And the balloon material is very, very thin. So to give you an idea how thin, so here's just a schematic of a piece of copy paper, which is about 100 microns. That's 100 millionths of a meter thick. A human hair is a little bit thinner. And the balloon fabric, the balloon plastic, it's called a gore. The balloon is made up, as you can kind of see from before. So the balloon material is made up of this very thin material. The closest analog you might have in your house is plastic wrap, literal cling wrap. And as you can imagine, that stuff's really delicate. You can easily tear and pull at that. These balloons, while they're able to lift several tons into the stratosphere, they're incredibly delicate and have to be handled with great care.
Question from the chat.
And they come in various different, sorry?
Question from the chat. Do you ever worry about birds or planes when the balloon is going up?
Sorry, I'm trying to get back a bit. That's a good question. Do we ever worry about birds or planes when the balloon is going up? It depends where we launch from. So when we launch from Antarctica, no, there aren't any there are very few flying birds and there are very few planes. In other areas, we actually do have to be extremely careful of airspace. So me as a scientist, my job is to build the camera, to build the instrument that attaches to the bottom of the balloon. The launching of the balloon is handled by NASA, the National Aeronautics and Space Administration, the people who fly rockets and satellites and things like that. And they have to arrange very carefully permissions. They have to watch out for birds, right? But they have to arrange very carefully for permission to stay, that airlines will stay away from that area and things like that. So we do have to be somewhat careful from that. These tend to be launched in pretty remote areas. Actually, I don't know of an incident with a bird, but I guess it's possible in some areas. I don't think it's very likely. Once they get, so that's only at the very beginning of the launch. The balloons very quickly are much, much higher than any bird will ever fly. So as long as there are no birds flying around it when you let it go, it'll be fine. So the balloon is made, I just wanted to show here these, when I say gores, what I mean is these sort of banana-shaped pieces of saran wrap that are very carefully bonded together along the sides to form a sealed surface. So these are fabricated on massive machines to make these long strips of plastic that all have to be carefully melted together to make the balloon. and packaged very carefully. And they're very thin, like plastic wrap.
There's another chat question.
And they come in all, yeah.
Sorry. Did you ever have to factor in the balloon gore getting damaged when budgeting for the mission?
Factor in the balloon being damaged or the payload?
The balloon gore getting damaged.
The balloon. So if the balloon is damaged, they try very hard not to have that happen. Every now and then this does occur. If the balloon is damaged and they don't notice it before flight, or it gets damaged after launch, then the payload goes up and comes down in a few hours or a day if the balloon leaks. And you know how the budgeting works depends on the payload, but generally you now have to spend some time and money fixing up your payload and put in another proposal for more money to fly again. There is an element of risk associated with ballooning. They're very reliable, and we've had generally very good luck, but you wait for the weather for a clear day to launch, and if something goes wrong, the payload comes right back down and you have to fly it all over again. So yes, balloon payloads are often made for multiple flights. So if there's not a perfect flight, you've kind of planned to do it again in the future. So this is just to say there's many sizes, and this is just saying this is the small NASA balloon, only 4 million cubic feet, versus the big 40 million cubic feet ones. And most of my work has been on the 30s and 34s. So these are able, if you have a lightweight payload, like half a ton, they can fly well above 120,000 feet. With heavier payloads, you can carry about 6,000 pounds of science and get to about 120,000 feet. Okay, so this slide is just to say that I'm not going to talk about all of these, and there are many, many more balloon payloads. There have been scientific balloon payloads from all over the world for decades and decades. There's many dozens. These are just a few to show that these are a few that are recent, launched in the past few years, that handle various wavelengths. So Anita looks at radio waves. Actually, it looks at radio waves produced by neutrinos. We can talk about that if you're neutrinos hitting the ice of Antarctica. You can talk about that if you're interested. Spider is one that I work on. It's a microwave telescope, so it looks around here. STO is a terahertz payload. That's kind of in this range as well. BIT is actually a visible light payload, and COSY is a gamma ray payload. So all these different regions where the atmosphere gets in your way, someone has tried to make a measurement from a balloon. And if I focus on the NASA program, which is the one I know best, these are launched from several places around the world. So you can launch a balloon. Most balloon payloads for astrophysics, for NASA science, are launched from the continental United States, actually, from Fort Sumner, New Mexico, or occasionally Palestine, Texas. These are areas where you can do overnight flights of a balloon. Anything more than an overnight, and you very quickly find your balloon, you have to be very careful that the balloon doesn't fly over heavily populated areas. There are regulations about that for safety in case something terrible went wrong and the balloon and the payload fell. You have to make sure no one's under it. So there are restrictions, and that's why you can't do very long-term flight. There's one reason you can't do week-long flights from the central United States, because you would get too far afield. There are also been flights from Alice Springs, Australia, which get you to observe from the southern hemisphere. Remember, you can see different parts of the sky from the northern and southern hemisphere, so it's good to be able to observe from both. Then there's a couple special locations. One in Sweden, the northern hemisphere, and the one I'm going to focus on is McMurdo Station, Antarctica, where we can do what are called long duration missions that last for weeks of flight time. And there's even a new technology I may talk about at the end that's launched from New Zealand. These are all NASA, but they're with partnership in different countries and different locations that can fly for months. So what I thought I would do, I can stop for any kind of technical questions now, but what I thought I'd do is give you a quick tour of what it's like to launch one payload from Antarctica. Just almost some pictures about what the experience is like. And before doing that, I should say there's, no one person does this. The Spider payload, this microwave telescope that I'll be talking about, I won't talk much about the science it does. But this is a big team spanning many institutions, including the University of Illinois. And this is the team that took it to Antarctica in the 2014-15 season. We're in front of, in the back, you can see Mount Erebus, the world's southernmost active volcano. And this is the view from the ballooning location. I'm often asked about the gentleman on the right, who is a grad student, who is clearly unimpressed by the cold weather that the rest of us feel the need for serious gear for. He's from Saskatchewan, so coastal Antarctica did not seem cold to him.
There is
so if you want
one technical question in the chat, Jeff.
Sure.
Do payloads ever land on private property? How is that handled?
Oh, you're getting beyond my knowledge here, because I fly mostly from Antarctica, where that doesn't happen. But we do have some control over where a payload comes down, and we launch in fairly remote locations. I don't know the exact regulations, but I know there are flyover negotiations that need to be gone into for these flights. This is mostly a concern for the North American flights, and I'm just not as experienced with those. But I've never heard of a payload not coming back because it landed in someone's yard.
Okay, thanks. There's one other question. I know people asked about birds and planes popping balloons, but at 130,000 feet, the temperature must be rising because it's thermosphere. Do these balloons ever just go pop up there?
Ooh, that's a really good question. You're correct. We're above the coldest point of the atmosphere, around the tropopause. And so the atmosphere is getting warmer. It's actually still colder than down here. We're not way up in the thermosphere. The temperatures up there are cold, but not below freeze. I think near freezing, not below freezing. It's a cold place, but it's not super cold. And because the air is pretty thin, you're not gathering ice or anything on it. I'm not aware of a balloon suddenly popping due to that. Unless it had torn lower down and already had a leak. One thing that is worth noting is when you're up there, because you're in space effectively, there's so little air, thermal management, heat management is actually a very big problem, because the sun is incredibly intense, and any part of your payload that is in direct sunlight will get very hot and has no way to radiate heat because there's no air. There's very little air. And any part of your payload that is out of direct sunlight, that is in shadow, gets very, very cold because it radiates to the black of space. And so you actually have to be very careful about thermal gradients, about parts of the payload getting too hot and too cold. This is something we all pay a lot, and this is also experienced for satellites that have to worry about the same thing. Okay, so suppose you want to take your payload to Antarctica. NASA has given you money, you've built it, you've gotten it ready. What does the process look like? Well, you can't go, there are multiple places you can launch balloons, but Antarctica, there's only 2 or 3 launches a year during the austral summer. So around Christmas time is when it's summer down in the southern hemisphere, and it's 24 hours of daylight. So to prove that your payload is ready to go, you first have to take it to East Texas, to the Columbia Scientific Ballooning Facility, which is named after the ill-fated space shuttle, Columbia. And they have a hangar there that is basically a duplicate of the facilities you will have in Antarctica. And so what you do is your team goes for the hot, moist summer of swampy East Texas and puts your payload together and does compatibility checks. Make sure that everything works, it fits specifications, and it communicates properly with NASA's control equipment, with NASA's flight and communications equipment. NASA provides to us the communication radios. So they're our Wi-Fi, right? They're our internet router that we have to plug into, and we have to test all of that out at a NASA facility in Texas. And so what you do is you do just what you will have to do in Antarctica. You have to bring your payload in crates. unpack your entire lab. That includes tools. You need to have tools, screws. There are hardware stores in Texas, but there are no hardware stores in Antarctica. You have to bring your entire lab with you. And you unpack from crates, you put the thing together. In this case, this is a big liquid helium tank that houses Spider's receivers. And you do various testing, and if you're lucky, you do some science, in this case, doing some measurements of the response of the telescopes. And then at the end of the summer, you throw it all back in the crates, and it gets ready for the long trip, either by plane or by boat, to Antarctica, where you will unpack it again in November. In this particular case, we did this in 2013. You may remember there was a government shutdown in 2013 that actually canceled the entire Antarctic season that year, because the little tantrum that occurred then in Congress prevented any of the logistical work from happening in Antarctica to send us when we were about to go down there. And so all of us, including graduate students who needed to write their PhDs and people like that, all had to stop and literally wait an entire year. So that entire season was canceled because of those few weeks. Those were critical few weeks to get the facilities set up, and we had to wait a year. So whenever people talk about government shutdowns, I give sob stories about how terrible this was. But we waited a year, and then this is what going down looks like. So you board a military transport. We have typically the Air National Guard, or sometimes the Air Force, takes us down. At the beginning of the season, these are on C-17s, enormous cargo planes. Later in the season, they are on slightly less, but still extremely enormous cargo planes, C-130s. The main thing that's nice about a C-17, which is shown here, is that it's a jet. And so the trip, you first fly from Los Angeles to Christchurch, New Zealand, where you get all your cold weather gear and wait for good weather. And on a good weather day, you get boarded onto a one of these military transports to fly to Antarctica. C-17s at the beginning of the season are great because they only take about 5 hours. And when the C-130s, which are prop planes, take about 8. And you really hope you don't have what's called a boomerang flight, where the weather turns bad and you turn around and come back and have to wait for another day. So you get to McMurdo Station, which is sort of a mining town kind of feel on the edge of the frozen ocean down there. This is the National Science Foundation's big station. You go to a high bay, just like we had up north, and put your payload back together, get the software ready to go. Get the payload ready to go at the hangar. If you're lucky, you visit some local wildlife, or at least the wildlife comes to visit your payload. Some of us grew unfortunate facial hair, but it was, it's a really incredible experience, very intense. Summer camp for scientists. You're just working all hours of the day. You sleep in a dorm. You go to the you eat in a cafeteria, and you do science, and you get this thing together because you're racing against the clock. The season is only so long, and you have to be ready because a day to launch a balloon that big needs to be perfect, not a breath of wind, and those are not every day. So you have to have when those launch days come, everybody has to be ready to go. And if you're lucky, our launch day was January 1st, 2015. This is the payload. This is the payload in the distance on the launch vehicle, which is like a big crane truck. This is the parachute that will bring us safely back to Earth. And this is the attachment point for the balloon. The balloon hadn't been attached yet. If it had, I would not be allowed anywhere near this. The balloon, as we saw, it's like saran wrap. It's incredibly delicate. And this package are the explosive bolts that when the flight is over and we decide to terminate and bring the payload back down on this parachute, those will pop open and separate from the balloon. And so this is what the payload looks like laid out. On the left is the Spider payload. That's the 3-ton object that my colleagues and I spent years putting together and getting ready for this moment. We are all sitting in the background by that building in the back right, utterly terrified, and just the most exciting experience of my professional career. And the balloon has been inflated at the top bubble, and is waiting for the signal to launch. And we had finally decided the wind was down, we were ready to go. And this is what a launch looks like. So we release the balloon from a sort of a pin that's holding it. So the balloon swings upward very slowly. You can see those little ribbons hanging off of it. Those are actually the fill tubes that were used to put helium in. They also allow a certain amount of helium to leak back out if the pressure inside gets too high. Remember, the balloon is very delicate. It can't sustain a pressure difference. And the goal right now is to release the payload when the balloon is exactly overhead. So it's a perfect, gentle release, and it sails into the sky. And so the crane drivers have to maneuver to get that perfect vertical release. And so look at the angle of that. You can see that the balloon is getting a little ahead of us, and so the truck is trying to catch up, but it's not quite working. That thing that fell is supposed to fall. It's called the collar. Don't worry about it. The truck is unable to keep up with the balloon. The balloon's got caught in a little extra wind, and eventually bonk, they let it go. It was actually a pretty rough launch, but a perfect one. That's supposed to fall too. Don't worry about that. Spider is aloft and in perfect shape. And so Spider took off on January 1st. This is the team of us in our Spider sweatshirts watching the launch. And this is, again, the view back toward the launch site from the GoPro camera on that first launch day when we reached float altitude. That's not Spider's science instrument. This is just like the tourist image, the PR image. But you can see we launched, Mount Erebus is that volcano. We launched near the windless bight, so we were kind of launching from around there. And people who are familiar with Antarctic history will remember names like Cape Royds, Hut Point, Cape are famous places in the history of Antarctic exploration. So once it's in the air, I guess it's been about 40 minutes, so I'm a little slow. But once it's been in the air, we communicate it with a variety of antennas, satellite links of various sorts. Spider's flight lasted about 16.5 days, landed us about 1,500 miles away. We came down when we ran out of liquid helium, and that keeps the detectors cold. The detector stopped working. This is a remote spot even by Antarctic standards, and our payload was found in the snow. There's a GPS tracker. We knew where it was. And the recovery of the data disks and later the hardware was helped by the British Antarctic Survey, who are based much closer to that location. So there's a certain amount of international negotiation necessary to get our payload back. And then we took some wonderful pictures of the sky, of the polarization of microwaves that I won't get into here at all, other than to say Spider worked fantastically. And we got we've got a couple science papers out about it. The biggest one was finally finished this March. Then a few quick words about other things in ballooning. So there is another kind of balloon that's called a superpressure balloon. That's a little more like a party balloon. It's actually sealed. It's made of tougher fabric, tougher plastic. And that means it's able to fly longer. Helium doesn't vent out. It's also the big difference here is that a zero pressure balloon of the type we described before can't handle a day-night cycle. You can see on the bottom, during the day, the gas inside, warms up and the atmosphere warms up and the balloon will float higher and inflate. But at night, when everything cools off, the gas will shrink and the balloon will sink. And so because the balloon varies in pressure, it rises and sinks and actually loses some helium, gets kind of squeezed out by this cycle each day. So it's hard to have a conventional balloon survive more than a couple day-night cycles. In Antarctica, we get away with flights of 2, 3, 4 weeks because there is no night. It's perpetual daytime at that time of year. The superpressure balloons can last for multiple days and night cycles because they are sealed. They actually stay at a pressure above the atmosphere, more like a party balloon, and can actually do very long flights, maybe as much as 100 days. And I say thicker, stronger plastic. The plastic is only about as thick as a sandwich bag. But these things are allowing us to do new scientific balloon flights that can go around the world. So this is a launch from New Zealand that went all the way around the world and then eventually landed in Peru for recovery. That was a 46-day flight of a gamma ray instrument called COSY. And that very long flight allowed it to get more data about the universe in gamma rays, which are invisible from the ground. They don't make it through the atmosphere. And in particular, to see by being able to stare at the sky for a long time and stare at a lot of sky from these latitudes, you could actually find occasional rare events like this gamma ray burst, which is a signal of a catastrophic stellar explosion somewhere in the universe. That you only get to see these things if you're looking for a long time with the right kind of instrument above the atmosphere. Another development that's kind of interesting, I think, are you can do optical telescopes. So there's actually a group that I work with some of these folks. I don't work on this project, but some of these people also work with me on SPIDER. This is a telescope, a standard optical telescope. You could do this from the ground, but this allows you, by going above to a space-like environment, you can take crisper images with no twinkling stars. And that images of similar quality to the Hubble Space Telescope, but at much, much lower cost because you're flying one of these balloons every now and then. This is a picture taken on a recent flight of an instrument called SuperBit. And you can think of this like a Steadicam. So the balloon, the system is hanging from a string at 120,000 feet, but there's all these feedback and control systems that actually lock the camera super steady to take a long exposure of the sky. And the vibrations and wiggling of the balloon make no difference at all. The camera stays locked. So this is another cool technology that's coming out that's enabling us to do more and more things from balloons. You may have heard that there's also been projects to do internet by balloon in remote areas. So there's a project by Google, or I guess Alphabet, the parent company, called Project Loon that has been working the past few years to set up super pressure balloons. So the exact same kind of ultra long duration balloons that can stay in the air through days and nights for hundreds of days. They built sets of these things and tried to deploy them to make a computer network that extended out into remote areas. They tested this a lot in Kenya in particular. And they recorded a record balloon flight of almost a year. This program, I'm sad to report, while it's super cool, was discontinued just a couple months ago. It turns out not to be cost effective. There's other ways of getting internet, like satellite internet, for example. So this is, but this was a cool project while it lasted. And I can answer more questions, but I just want to say in closing that these kinds of science projects, I wanted to list that several of these are going on here at the University of Illinois. These are the 3 NASA astrophysics balloon payloads that are currently being worked on at Illinois. SPIDER is the one I showed you. This looks at the glow of the early universe, the cosmic microwave background. And members of my team here at Illinois have worked extensively on building the telescopes, and it's awaiting for its second flight, which we are eagerly awaiting when the pandemic has canceled the last couple of balloon seasons, and we're eagerly awaiting the next. TIM is a newer project that's going to look at the history of star formation in our universe, the assembly of the of galaxies, these periods where the universe went through a sort of growth spurt of rapid star formation billions of years ago. TIM will observe the history of that from a balloon. Again, things that are hard to do from the ground, or impossible in both cases. And just 2 days ago, we got news that a new payload that I work on has been funded by NASA called Taurus. That is also a microwave background payload. This will be on one of these super pressure, ultra long duration flights from New Zealand that will go around the world and observe the sciences. Essentially, you'll observe the fogginess of the universe after the CMB, which will tell you something about a few things, but the most important is what the universe was like, how the first stars turned on, the history of the very first stars turning on and burning away the fog of the universe, so to speak, ionizing the neutral gas of the universe. So these are 3 big payloads that are being worked on by groups here at Illinois, and I hope you hear more from each of them in the future. So that's all I had. I'm happy to answer more questions. Just to say that I've only shown a small amount of the kind of science that you can do from these. I've talked mostly about the experience of flying these things. We're very excited as the balloon season the whole balloon season everywhere was canceled last year, understandably. But the balloon season in Fort Sumner is about to kick off this summer, and Antarctica will be in the coming year. And so this science is about to resume. And with that, I'll say thanks and hang around for any questions.
Okay, great. Thank you for that, Jeff. Does anyone have any questions? Please put them into the chat on YouTube and I will relay them to Jeff. And while we wait for people to get some questions together, oh, here's one. What are some differences between the first and second Spider payloads?
Okay, yeah, so we flew it once, we had a great flight. Why would you do it again? I really haven't talked very much about Spider in terms of what it does, but it observes a particular signal in the glow of the early universe, the cosmic microwave background. But that signal can be obscured by the glow of our own galaxy. We are embedded in this vast pinwheel of hundreds of billions of stars and gas and dust. And in particular, that dust can emit similar kinds of microwave light and obscure the signal from the early universe we're looking for. It's as if we're always, even from a balloon, we're looking out through the cloud of our galaxy. What Spider 2, in particular the telescopes made here at Illinois for Spider 2, what they're designed to do, they observe the sky at a different frequency. And that will, it's like observing this, it's like you're making an image with multiple colors. And what this will let us do is distinguish the glow of the galaxy that we don't want from the glow of the early universe that we do. So it's to remove the contamination of galactic dust from our pictures, to give us a good map of galactic dust to tell us where not to look, so to speak.
Next question, what happens to the balloon itself after the payload is released?
Yeah, it's a good question because it's a big piece of plastic. I believe they're designed to, when they're released, to tear in a certain way so that they kind of fall. Actually, never heard someone explain to me in detail. I believe they're supposed to tear up a bit, and they. I know that NASA puts a great deal of effort into making sure there are no animals harmed from these plastics, but actually, it's embarrassing. I actually don't know a good answer. I'll have to look it up.
This one is not a technical question. Did you guys name the penguins?
Did we name the penguins? We didn't see very many. I didn't name the penguins. This one you see here, this is for penguin aficionados. This is called an Adelie penguin. So these are small, like, they're little guys. There also are bigger penguins called emperors, the very biggest penguins. They're more like 4 feet tall, 3-4 feet tall. We saw one emperor the whole 2 months I was there, and it was, you'd think people work in Antarctica and they would be used to seeing penguins. But when the emperor penguin wandered by the balloon facility, one of the grizzled old guys ran in, is like, penguin, and everyone ran out to look. There's a lot of excitement associated with these things. I don't think we named them, but we were excited to see each and every one of them. My son is apparently not excited at the moment. If you can hear that, the penguin here, the reason I like this picture, you can see we have a lot of pictures of him kind of walking funny. If you think about the world from the point of view of a penguin, they have never stepped on any surface that is not snow or rock or water, right? They've never been on anything that isn't snow and ice or rock. And so this is a wood, obviously a wood platform. We call it the dance floor. It's used for, you put the payload out there for certain testing. And he just kind of wandered around there super confused for a long period of time. It was hysterical because he'd never walked in anything that was like that. Yeah, anyway, penguins are fun, but we are not allowed to get near them. We are not allowed to touch them. Don't ask, nobody eats them. No one can bring any home. There are very strict wildlife protections on penguins. But they're also not afraid of people. So you're not allowed to walk near them and you're not allowed to touch them, but they do often walk up to you. It's pretty neat.
Next question. Is there any way to do active station keeping with the new long duration high altitude balloons?
That's a good question. So balloons in general, if you think about it like sailing, the balloon is huge. It has an enormous area of a sail. And so the wind at high altitude will blow it wherever it's going to go. And the balloon is very thin, so you can't like pull on it hard. And you could imagine putting a propeller or something, but the air is so thin that the propeller wouldn't give you much force. So these things are incredibly hard to steer. More or less, the reason we launched from Antarctica, actually, I don't think I made that especially clear. The reason we launched come on. I'm trying to get to the, sorry. There we go. The reason we launched from Antarctica is it's a convenient circularly shaped patch of solid ground. And even though we can't steer the balloons, if we launch at the right time of year, a circumpolar vortex, the polar vortex, will spin it around Antarctica and keep it over land for extended periods. Anywhere else in the world, it would go over people or deep over the ocean. And here, even if we can't steer it, we can control it. You will note that I think I noted that the loon balloons are somewhat maneuverable. Some of that is just by changing height. Like they had a mechanism to be able to alter their height a little bit by changing the pressure in the balloon. And that would let you, if the winds at different altitudes are going in different directions. So you can to some extent maneuver by just choosing to go down or up into the correct wind stream. But it was my understanding was kind of crude, though I'm not an expert on these. The scientific balloons are basically non-maneuverable.
Okay. Does anyone else have any last questions for Jeff? Has climate change affected balloon science in any way, or will it?
Ooh, that's a good question. The main effects it would have. Now, I am not a climate scientist. And so, the two things that one could imagine is by changing the temperature profile, you could change that polar vortex. We rely upon that circumpolar wind pattern. And insofar as weather patterns can be disrupted by changing climate, you might worry about this, but I am not, current on what this is. You worry about could there be changes in the wind pattern might change where you want to launch from. And how often there are windless days in each location. So the balloon will be up once you launch it, it's up very high. But the process of those wind patterns, we live and die by the wind, both on the ground to let us launch, and then at float to have a controlled trajectory, or at least if we have a reliable trajectory, we can't control it. So, for climate change, a concern would be disruption of those wind patterns. And also practical things like when we fly to Antarctica, we have to land on ice runways. And if those become harder to maintain due to changing temperatures, that affects the logistics of getting in and out, period.
Okay. I don't see any other questions. So now is your last chance if anyone else would like to ask anything. Thank you for giving this talk, Jeff. That was really, really great. Not very often that you hear about people going to Antarctica. And thank you to everyone who came to Astronomy on Tap tonight.
Thank you.